welcome all. I hope everybody had a pleasant summer. We've had a very busy summer and early fall. As people who follow our updates might know, I was just in Prague for an exciting meeting on our proton boron work, which has pretty suddenly moved from a fringe to part of the mainstream. We actually had 100 researchers from all over the world, most of them working on laser applications of proton boron fusion for the simple reason that those machines are already built. And we've been doing a lot of work preparing for the start of our own proton boron experiments in the lab, and I'll say a little bit more about that later. So the main point of this session, as advertised, is to see whether we can do some laboratory demonstrations to convince everyone of the reality of magnetic force fields. So as Obi-Wan said, there is a force pervading the galaxy that affects everyone, both living things and non-living things, actually, and that's the magnetic force field, which is everywhere in the universe. So what I'm trying to do is to demonstrate that this force field is real. It's not just a mathematical creation. It is able to convey angular momentum, and it has energy. Well, the first thing is the basic idea that Faraday came up with, that there is such a thing as a field of force. So the idea of a field of force, and this is really very much like a field of wheat, is that everywhere in space there is a direction and a magnitude for the magnetic force field. So this can be imagined as a field of vectors pointing in various directions and with various lengths. So that is real. To visualize this, we can use what are called magnetic lines of force. A magnetic line of force is a mathematical fiction or mathematical concept that simply connects at every point the direction of the magnetic field. So basically, the way we can easily see this is if we take our little neodymium disk magnets and you put them vertically under a piece of paper, ideally a piece of white paper. And if people have the equipment, try this. And what you do is you take the salt shaker full of magnetic filings and you just shake it onto the paper. And as I say, this works much better if the disks are vertically aligned. And once you have a little magnetic filings, a little iron filings, the disks will be attracted to the iron filings, so they will be able to stand up. Here you see the one magnet, and here you see the other magnet. And what I've done is just distributed the magnetic filings so that they're starting to line up with the magnetic field. So
when you say the disc vertically, the magnetic discs vertically, do you mean like on their sides?
That's right, on their edge. Okay. Because the magnetic disc has a north pole on one flat side and a south pole on the other. I think I'm going to disrupt the pattern, but people have seen it. So, see, they're not quite easiest thing. Whoops, they do stand up on their own because they're attracted to the magnetic filings. But now we've sort of destroyed the pattern because the magnetic filings have to be spread out or they'll just go on top of the magnets. But the part that's on top of the magnets, you can see the three-dimensional pattern, that this is not a pattern in two space. It's just because we have a piece of paper. It's actually a pattern in three space.
Well, we have something kind of in the same idea. We put our whole row of magnets just
Oh, wow.
in a long line.
Right.
And this is what we got. Can you see it?
Okay, great.
So you can see clearly two circles. And also the little shavings are sticking out of the paper, at least some of them are.
Because I mean, well, I'll ask you, why are they sticking out of the paper?
Oh, you know, it's just that the vertical dimension is also part of the field. It's like a cylinder.
Right. The field line is going out of the plane of the paper.
Yeah.
I got one.
Oh, wow.
Wow.
How many of that? That's three?
That's 3 groupings.
So each of them is more than one magnet.
So this is like 2 magnets. This is like 2 magnets, and this is like 4 or 5 magnets.
Okay.
And so you have a sort of a cool, you can see it's like a torus almost. You have this sort of central grouping, and then you have each one has a space around it.
Let me ask people, I mean, in the last session, some of you, I forget who, sort of raised the question, is there a difference between a field and simply the force between two particles? And to me, this is convincing evidence that there is definitely such a thing, because you can see that if you continue to hold it up, Sam, the lines of force do not directly connect the magnets. They obviously bend in space between the magnets. So I'm going to ask, is this a convincing demonstration that the force field has an independent existence and is not simply our way of describing the force between particles?
I'll answer because I think I was the one that had the question. And the question was really about, I didn't really understand the difference between the electricity and the magnetism. And in actual fact, I was thinking about this and I came to the conclusion that was where I was wrong. The electricity and magnetism are always linked. So you have a look at these lines. What causes that white space? What causes the gap between the magnetic field lines? There is some force pushing those filings away from one another. And I don't believe it's the magnetic force, because the magnetic force aligns the filings between the North and the South Pole. So what I think is happening in there is there's an electric field wrapped around those magnetic fields causing that gap. See, I asked this when I was a student back in the day, and the lecturers didn't really tell me. But there's something is causing that white gap. there's a force. And
All right, can other people, does anyone want to answer Ron's question? So we're talking about the gaps between these filaments, let's call them, or lines of magnetic field, and the gaps around the magnets. Is that what you're talking about, Ron?
Correct.
Okay.
Yes.
All right. Does anyone want to offer an explanation? Just speak up. Yeah.
So basically, it is the strength of the magnetic field that's aligning. The charge field is aligning the electrons within the iron to the electrical charge of the magnetic field. So whereas you see that gap in there that's literally too strong for the electrons in the iron filings or whatever the ferrous metal is to be within, but it wants to align positive to negative, as that's, you know, how magnetic fields work and magnets in general.
Well, okay. Anyone else?
Yeah, my interpretation of it is that once you put the filing on there, that becomes like a mini magnet when it gets magnetized, and therefore each of those little pieces of filing will push away. They're both going in the same direction, so they'll push each other apart and leave a gap.
I think it's slightly different to that.
Right. Yeah. Basically, that's right. In other words, let's go back. Okay, Ron, you had something else to say? Ron, you're not, you're muted.
I don't believe
Can you
that's
hear me?
what's pushing them apart. The magnetic force is causing the filings to all line up along those field lines to reveal them. That's the direction of the magnetic force. This force is at right angles to that force. And in electromagnetism and in the field, I think the only force at right angle to the magnetic force is going to be an electrical field. So I think whenever you have a magnetic field, you're going to have an electric field and vice versa. They are never found separate. And I think that's helped me a lot understand this whole thing. It's electromagnetism.
Okay.
I think it's a simpler explanation for the. Can you hear me now?
Yeah.
Oh, right. Okay. I've been fiddling around with my microphones and I finally found one that's working. I think it's a bit like Sam said. I think each filing becomes a magnet and attracts. Therefore, the filings attract each other because each of them is a magnet. So they line themselves up. They self-organize, if you like.
Right.
The gaps between those lines are simply because you can't have that. There isn't enough filings to cover the whole piece of paper. So where they line up, they leave, where they attract each other, they leave gaps behind them, if you like. I don't think it's anything to do with electrical
Right.
field.
Let's try and see what I've got here. Okay, so people can see my pattern now?
Yeah.
Okay, so I've put more, the filings, not more filings, but I put them denser in the middle. And you can see, as Peter says, it's only in the periphery where there's not enough filings that you get these gaps. The gap around the magnets actually disappears when you have enough filing. What you get instead is a gap in the middle. And again, it's because the magnetic filings are being pulled into the stronger area of the field. And I think I can show this I am going to turn this magnet around. Right. And now we see the north and south poles are attracting each other, and the field is strongest in the center, and we no longer have the gap. So basically what's happening, as Peter says, the iron filings are, because of their ferromagnetism, are becoming little magnets in the magnetic force field. This is not something that any metal can do. It's only that ferromagnetic metals. So that includes iron, nickel, and a few others I don't remember, but those are the most common ones. So let's try and look at what's happening. First of all, as I say again, these are aligning with the magnetic field. So what's happening is there are currents flowing within these magnetized neodymium magnets. They're currents formed because the electron orbits are aligned with each other in a magnetized body. If we simply imagine that these are electromagnets, which they certainly could be, it just would be more complicated, then all we would need is a coil of wire with a current running through it. So a magnetic field can be produced in two ways. One is by a current of charged particles. So if we go back to Maxwell's equations, they have a term in which B is related to J. So J is the current density of moving charged particles. Now, Ron is referring to another way that magnetic fields can be produced, which is a changing electric field. An oscillating or any change in an electric field produces a changing magnetic field. So that's the term that relates the electric field to the magnetic field to dE dt. So the rate of change of the electric field. Well, that's not relevant here because the currents in a magnetized body are basically very stable. So we're not getting a change in the electric field. In a demonstration we're going to do in just a moment, we will see that change in magnetic field and electric field. But what we're seeing now is that the field, and again, I want to emphasize this is a real thing. This is a process that exists everywhere. In all points of space, there is a magnetic field. And if you have a ferromagnetic body, that body will align and show you the direction of the force field. So it's demonstrating that these field of vectors that was first hypothesized from Faraday and was the first big departure from the Newtonian idea of particles affecting each other by forces that align with their centers. This is a field that exists, and that the direction of the field is created by currents according to Maxwell's laws, and as our demonstration shows, they don't line up with particles. We have, as Sam can see in its diagram, there are lines of force that are very far from a straight line between the magnets. There are curving lines of force that are created by the electric currents, as described in Maxwell's equations. So that's point number one. So first of all, do you think that's an answer, Ron?
Well, I do and I don't. I mean, I can see what you're saying about when you clump the iron filings together, but I don't think that's actually, how do you say, you've turned it into a solid. Now, if there is a electric force acting at right angles between the particles, it's within the solid. I mean, you've got the same thing happening within the solid bar magnet itself. The magnetic field is caused down at the atomic level somewhere, probably within the atom. And it's the spinning charged particles that have caused an electric field, if you like, from the atom or within the nucleus somewhere. And there's a magnetic field in there as well. Now, in magnetic materials, clearly there is some kind of unbalance so that the magnetic field becomes apparent outside of the atom. But with paramagnetic or non-magnetic fields, there must be kind of a balance between.
Well, Ron, but let me just correct you here. We are dealing with magnetic force field, not an electric force field. As you say, they're independent. The electric force is at right angles to the magnetic force only when we have changing magnetic and electric forces. So that's when we get that. We also get that the magnetic force can produce perpendicular electric forces on moving charges. But what we have here is actually magnetized magnetic force field that's affecting the iron particles. They're reacting to the magnetic force. So the electric charges within these neodymium cancel out. There are an equal number of electrons and protons within all of these. So we don't have charged bodies. We can, in a second, I will get to a charged body. But here we don't have electrostatic forces. These are magnetic forces that are created by the motion, the currents moving within these magnetized objects. As I say, we could do the exact same experiment without neodymium, with ordinary copper, if we simply put the copper in a coil, and that will produce an electromagnet and a magnetic field that will look pretty much like this. So if we move away from, I don't want to get into the discussion of ferromagnetism. It's an interesting topic for a future class, but it's pretty complicated. The main thing is we have a net current, a net electrical current, and that current is directly creating the magnetic field. The magnetic field is operating on the same electrical currents that occur in the iron when it is exposed to the magnetic field, and that's what magnetizes. So let me go on to the next demonstration. I hope at least this convinces people that there is such a thing as this magnetic force field, that it is a real thing, and it's not just a mathematical creation. And I want to emphasize the lines of force are a mathematical creation that enables us to visualize what the force field looks like. The force
this
field,
visual,
as I say, Peter?
I was just going to say that this visualization only really works because of the friction between the paper and the iron filings. So if they were able to move around freely, they would all just move along, I guess, along the field lines and end up at either end of the magnet.
Right,
So
right.
you could do this experiment. It'd be quite interesting to do this with iron filings suspended in a solution, drop a magnet in it, and watch the particles, the iron filings move.
Well,
I've never seen that. It'd be quite
if
good.
you give me two minutes, I think I forgot about this little thing, but I think I can show you that.
Oh, right.
Give me a
Cool.
minute to come back from another room.
You've got one of those shakers, like you have the snow falls
It's probably got some magnetic fluid. And
something like that.
I've got a little
Yeah.
bottle like that with a magnetic fluid, and it's really quite interesting. You put a magnet near it, and the magnetic fluid moves in the fluid. It's quite insane. But I'd love to see this experiment done in space with no gravity, so that
That's very similar to a fluid with suspended
to a
particles,
fluid, yes.
isn't it? Yeah. I mean, Sam, you've got a pretty artistic piece of physics there now.
But yeah, it's nice. I'm also like, if I disturb the paper a little bit, I don't know if you can make it out exactly, but you can actually see the filings like following the field lines towards the center.
Yeah. Yeah.
Let me see if I can do it like here on this bottom one. So if I have like these down here,
Eric's still looking
It
for
wasn't
his
in another room.
and then I start to sort of
Okay.
jiggle.
All right. So here we have a solution of magnetized particles. And here we have a neodymium magnet. So if we put this it's attracting and nothing interesting is happening. But let's see.
You're slightly out of shot. Oh, there you go. Brilliant.
Been a while since I played with this. Okay. So what you see is so they're starting to move through the liquid as they're attracted to the magnet. And they're becoming magnetized. And if you...
Oh, yeah, got it.
Now you see they formed a pattern. Now, what's keeping them into that pattern, Ron?
Can you hold it a little higher, Eric?
Okay. Well,
what is inside that liquid?
It's a chemical that keeps the iron particles in droplet form. I can't tell you the name of the chemical. This is a toy that we gave away as a prize in our first fundraiser on Indiegogo. I will have to, in a future session, advertise the maker of this thing because it's really quite an amusing toy. So let's see whether we can get this right. If you Okay, now you can see it. There are a number of dots, right?
Mhm.
So these dots are magnetized, and the force of attraction to each other is balancing their force of mutual attraction to the big magnet. If I draw the magnet closer, then they all get attracted and form a single blob. So this is, again, you can see in a continuous medium that their force of attraction to each other can be balanced versus their force of attraction to the magnet. Of course, if you take away the magnet, they're no longer magnetized. So you see the gaps between them, Ron, are not being caused by repulsion. It's being caused by the balance between their attracting each other into clumps and they're being attracted by the big magnet, the external magnet. So, okay, well, we can come back to this later, but I wanted to go on to the second demonstration, which is demonstrating that a magnetic field can convey angular momentum. And again, this is something that is purely due to the fact that magnetic forces do not operate along straight lines. All right. So if you have a battery, this is a AA battery, you put 3 or 4 on the positive end of the battery. Then you take your wire and you bend it. I mean, this is the craft part, which I'm not that good at. Probably you're better. You bend it into a shape sort of like this. So it has a double bend up here and is curled around like this. Darn. Well, I think it spins for long enough for you to see that it's spinning, right? All right, so has anybody else done this? Maybe they can show a better demonstration.
See it? Yeah, you can see it now. See it?
All right, but it has to be touching. So the battery end, the flat end of the battery is here.
Yeah.
The positive end is attached to the magnets.
Okay.
For this demonstration to work, you have to have the copper touching the battery on top and touching the magnets on bottom.
Got it.
That
Okay.
means you've got a complete circuit. And if you have a complete circuit, the current is flowing in the magnetic field of the magnets, and that creates an azimuthal force, which conveys angular momentum to the ups, but it keeps spinning off. That's the problem. So you have to make sure that there's a complete circuit from top to bottom. Oh, here it goes. Oh, again, as soon as I tell it, if somebody's looking at it, it will fall off.
Sounds like a quantum effect.
Yes, like
Oh, that was
a fake quantum effect.
Right.
All right.
Oh, here goes ours.
Okay. Let's see yours. Okay, but is it touching?
Oh, it was, and then it.
Yeah. Now the cleverer way, is you make it longer and then you twist it into an actual loop.
Yeah, yeah.
But it's a little difficult to get the friction right because that can easily produce too much friction. So let me try that one. It also has to be balanced. That's the problem with mine. It's a little bit unbalanced. Is anybody else trying this?
I'm trying.
Make a little coil at the bottom.
Sam, you're trying it?
I'm trying. It's hard to get it to be the exact. The balance, yeah, is tricky, but I'm getting there.
Well, if you look at the people who were doing this correctly on other videos, they do have a bit of a loop at the end. But as I say, the problem is the contact is best if it's the very end of the wire that's contacting, not the side of the wire. Even though these are uncoated wires, the sharp end makes a better contact. They're so delicate. I actually, people can believe me or not, had this spinning like crazy last night. But copper is such a soft material, the wire bent out of shape on its own.
Any good demo fails when the audience is there?
Yes. Just as in what we will describe as the fake notion of quantum theory. In the real quantum world, it doesn't matter whether you're looking.
Mine is only one end of the wire is touching, but it's spinning slowly.
Right, but that can be just from the fact that you have a small amount of friction.
Right.
If it's connected, it will spin faster and faster until it falls off. All right, so what's the trick there?
Well, I'm using a desolder braid and kind of just getting it to kind of make contact. Basically using the electronic motor principle. I got a little bit of a flat top on the negative part of the battery that's keeping it kind of in place. And as you can see, it's kind of a curved heart shape. And it likes to go out of
Oh,
limiter.
look at Elliot's.
Let me see.
Yep, there you go. He's got it. He's got that big curve.
Can you turn it down, put it down a little, and then we can see it. Down further. Oh, great. Great. Wow.
That looks like a helicopter.
Yep.
Oh my God. How expert is that? So what did you do on the bottom? Is it a complete loop?
It's a loop that kind of just springs on the one side is just maintaining contact with a little springiness.
Okay. So we have two contestants are going, one fast and one slow. So the key thing, other than the fact that experimental work needs craft skill, that we learn from this is, where is that angular momentum coming from? We all know angular momentum is conserved. So where is the angular momentum coming from?
So let's see, you said there was a change in the electric field.
Now, again, this is a magnetic phenomenon.
Oh, this isn't that
There's
one.
an electric current. So there's an electric current flowing in a circuit, as electric currents do. So the circuit is, the current is being generated by the battery. So the current flows from the top of the battery into the magnets, which are conducting. From the magnet, it flows into the copper wire and then back to the battery. So that's the circuit.
Oh, okay.
So what's happening, though, is How is the
cross B.
circuit conveying angular momentum to the wire? Where's that angular momentum coming from?
That was Maxwell's law, E cross B. So you got an
Right,
electric
you've got an
field.
E cross B field. So you've got the B field is perpendicular in the to the wire, and the current is flowing along the wire. So the force is perpendicular to both. So the force is azimuthal. The field in this area is horizontal. The current is vertical. So what's perpendicular to both is the azimuthal force. So that's correct, Ron, is that it's the E cross B force that's doing it. But where is the angular momentum then coming from? Well, remember, angular momentum is conserved. If something is spinning in one direction, something else has to be spinning in the other. I mean, let me just, if we put the device onto a platform that's allowed to spin, what we would see is the magnets and the battery spinning slowly in the opposite direction. Slowly, because they have much more mass than the wire. The wire, of course, is much lighter than this. So angular momentum is being taken from the battery and the magnet that's attached to it and being given through the magnetic field to the copper wire. And that's an extremely important phenomenon because, first of all, a magnetic field can convey angular momentum. A gravitational field, Newton's point-to-point field, cannot convey angular momentum. If that wasn't true, none of us would be here because we wouldn't have a sun and we wouldn't have a planet. When objects contract in space, remember, the sun has formed from a cloud that's approximately half the size of the distance to the nearest star. Nearest star is 4 light years away. So the sun started life as part of a cloud that was maybe a light year in radius. Now it's only 1 million miles, 1 million kilometers in radius. So even if that cloud was spinning very slowly, once every 200 million years, like the galaxy, it would have tremendous angular momentum because angular momentum comes from the product of mass, velocity, and radius. So as it contracts, if it's going to keep on contracting, it has to get rid of that angular momentum. And what Alfvén and Falthammer demonstrated decades ago was that it is, what happens is there is a background magnetic field of the galaxy, which is a few millions. We have the homopolar effect in which a charged, a conducting body rotating in a magnetic field creates currents that move to the center. So these currents create their own magnetic fields, and those magnetic fields convey angular momentum from the center of the body to the outside. So the gas on the outside starts spinning faster and faster and is continuously blown off, while the gas on the inside loses magnetic angular momentum and contracts. And when the star gets, the protostar gets close enough, gets dense enough, we have another phenomena, which I'll have to get into in the future, which is the formation of a plasmoid, just like a plasmoid we form in our device. A plasmoid emits beams, and the object becomes what's called a Herbig arrow object. And these beams are very rapidly spinning beams of plasma, and they rapidly carry off the remaining angular momentum. So what happens is the innermost gas carrying most of the angular momentum that remains, a very tiny fraction of what you started with, form the planets in a solar system. So for example, in our solar system, even though the sun has almost all the mass in the solar system, the angular momentum is carried mainly by Jupiter, because Jupiter is so much further from the center of the solar system. So that's allowed the sun to contract so much that it heats up and starts to produce fusion energy that eventually leads to life. So that process, again, the magnetic field is this real thing that can convey angular momentum and convey it, obviously, in a direction that is not aligned with the direction between two objects. So is that clear? Any questions on angular momentum? And somebody's is still going. You have to stop it and show us the magic shape. So it's a big heart. You see, it's considerably bigger than mine. Hold it up a little.
But
Right.
but also
It's a
the
big
bottoms
heart with a very big loop. So people have to start over with clearly more wire. And I can see why yours works better, because yours has a greater, what we call moment, well, it has a greater mass and a greater moment of inertia. In other words, it's mostly further out from the axis. That gives it, and a lower center of gravity, possibly, yes. That's a good point, Martin. Yeah. So that's a great design. You should make a photograph of it and share it.
Okay. Yeah, the trick is the bottom is hooked. And so one of the bottoms ends up going around the magnets and maintaining contact.
Yeah.
It's probably the balance. I don't know. I'm not sure.
Well, as I say, it's also that yours is a lot bigger.
Yeah.
So it goes further out, and that gives it more stability.
Right.
So the third demonstration is the question that, and this is again something that's really remarkable to the average person. Magnetic field contains energy. It not only can convey angular momentum from one point to another, it itself contains energy. And I think we can demonstrate this fairly dramatically. We're taking the magnets off the battery. We don't need them for this demonstration. So we're going to lay the battery down here, and we're going to connect the wire to the battery. So the current is flowing from the battery around the wire and back. So there's a very small magnetic field with a very small amount of energy in it. And when we are about to break that, the current is going to fall. The magnetic field is going to fall. And that means, as Ron pointed out, you're going to generate an electric field. So, but because the magnetic energy is proportional to B squared, to the square of the magnetic field, we're not going to be able to see this effect. And nothing much will happen. So here I am breaking the the contact, and we don't see anything. Now, we have a way of greatly increasing the magnetic field with the same current. This is a inductor. For you, those of you interested, it has 10 millihenries inductance, which is quite a bit. And all this inductor is, it contains no energy source itself, it is a wire wrapped many times around a iron core, which increases the inductance. So the inductance is the ratio of the magnetic field energy to the current squared. And I don't know whether people can see, I hold it up close. Can you see the wires inside this? Over here, sort of peeking through. I don't think we have enough light. But take my word for it. All that's inside here is a lot of copper wire wound round and round. So why it's important that it's wound round and round is that increases the magnetic field. So just imagine if we put this into a coil, the magnetic field of this piece of wire is added to the magnetic field of this piece of wire. So the magnetic fields that go in this direction, they cancel, but in the vertical direction, they add up. So this is what's called a solenoid. A solenoid has a magnetic field that depends on how many turns there are. In addition, and again, I won't get into the details of ferromagnetism, the fact that you have a ferromagnetic substance on the inside, that increases the field more. But we've got less current because we have more resistance here, because you have to go through more turns of wire. But we have much more energy in the magnetic field. So we're going to do the same experiment, but we're going to connect the wires to the ends of the inductor. And then we go back again and we start the current flowing. And now we break the current. Do you see what's happening here?
Sparking.
Right. You can see that? Can everybody see the sparks? They're not that big.
Look right at the edge of the loop if you can't see it.
Okay. Can you now see it?
Yeah.
We're getting sparking at both ends. Actually, this might be a little easier to see. Let me just reverse. So we're getting a slightly bigger spark from the alligator. Do people see that now?
Yes.
Yes, yes,
Yeah.
we can see it. Yep.
Now, I do have a 12-volt battery. So now we're attaching to this much bigger battery. 12-volt battery.
Eric, don't forget to move the neodymium magnets further away from that battery.
Why?
Because the arc could jump to the magnetic field.
Oh, no, it's not going to be that big. The main problem with this is that there's too much current for the wires and they begin to heat up very rapidly. So,
those are really thin gauge wires. They look thicker than they actually are.
yeah, so we're not going to maintain the current for very long, or else I might burn my finger. Am I oriented correctly?
Yep, we can see you.
All right. Presumably people can see that spark, right?
Oh, yeah.
All right, yeah.
It does actually go that
The
far.
paper really should be further away. So basically what's happening is that during the brief time I have this attached, of course, the current starts to flow instantaneously. And when I move it away, the current suddenly falls. So the current in this big inductor falls, the magnetic field falls, and the very large amount of energy in the magnetic field generates an electric field that is big enough to create this spark. And basically, we know approximately how big the voltage has to be if we know how long the spark is. So the spark to me looks like at least of the order of 1 to 2 millimeters. And you can also see the energy in the spark. I think people can see that there's a significant amount of localized melting on the disc, the copper discs. So we're developing enough energy to melt a tiny amount. Now it's probably vaporizing some organic material because we're getting black soot. So there's probably a small layer of organic material on this that's vaporizing. So to break down air takes about 40 kilovolts per centimeter. So if the spark is 1 millimeter, we've got about 4,000 volts generated by the magnetic field energy stored in this inductor. Oh, wow. Okay. So again, before we start a fire, I hope that convinces everybody that there is energy in a magnetic field, because obviously, as I say, with the smaller demonstration, the only difference between getting no spark and getting a spark was that the current was flowing through the inductor. When the current was flowing simply through the wire, you have a much lower magnetic field. B squared is much lower, and therefore the total energy stored is much lower. So when the energy is released, when the magnetic field goes to zero, you don't get enough voltage to create a visible spark. So, okay, so questions and comments. Is that a good demonstration that magnetic fields are not only real, but they store energy? Martin says he's convinced. Okay.
Yeah, I'll buy that. Yeah.
All right.
Are we too far back yet to talk about Tesla coils, or are we right there in the same time frame?
Well, obviously we're in the 90s. Where we left the story was around 1890.
Yeah, so we're a little far back for it yet.
Tesla obviously was what, a boy in 1890?
Yeah, he would have been like 7.
Yeah. So this is sort of the science that by the 1890s, the science of magnetic fields had developed to the point where you had very efficient electric generators and very efficient electric motors. So electrification of cities in the most industrialized countries in the United States, in England, was rapidly progressing by this time. People did not use directly solutions of Maxwell's equations, which, as I have said many times, are very difficult to solve mathematically. They used the concepts embodied in Maxwell's equations to steadily improve the efficiency of magnetic motors. And of course, what we have here was a primitive motor. We were converting electricity into kinetic energy, which could have done a very small amount of work. In other words, if we had attached a thread to at least the most successful example of the spinner, it would have wound that thread up, or could have lifted a mosquito-sized weight. The same basic concept of magnetic fields conveying angular momentum works in actual electric motors that are driving now, powering millions of cars. And the efficiency of these motors is such that, of course, these motors are much more compact and, a factor of 5 more efficient than internal combustion engines. Internal combustion engines mainly generate heat. Only about 15 to 20% of the fuel you put in an internal combustion engine gets converted into kinetic energy.
5%.
But the what?
It's 5%. The internal combustion motor is 95% inefficient.
It's only 5% still? I thought it would improve.
I mean, if you have a high-end vehicle, you can probably get up to like 7 or 8, but I don't think we've broken that 10% yet. I'd have to look it up.
So electric motors can easily be designed up to something like 98 or 99% efficient. So you have, even though you have a problem with efficient storage of electric energy, I'm sure they will not stick with lithium batteries.
I hope not.
Need far less energy to drive an electric car than a gasoline-based vehicle. And that's why, on a fuel basis, even with the present elevated cost of electricity, the fuel cost of an electric car is much less. So,
to put it into perspective of when we were doing the battery with the wire around it, he had it spinning so fast, he has 1.35 volts in that AA battery. So imagine now if you had a 12-volt battery or a 24-volt battery, and then you had a wire that was locked into place, you could move some serious stuff with that. So that's where that comes from.
And yeah. And I think that other technologies are definitely coming down the road. At some point, we'll talk about ultracapacitors. So for the final demonstration, this is something that Brian and I could not come up with as a live demonstration. I wanted to go to the other side of the story, which was the discovery by J.J. Thomson of the electron. So, Brian, you said that you had found some videos. If you could, I didn't have time to look at them. So if you could just select the one that you think is best. How many minutes is it?
Altogether, I'm going to say that with the 4 videos, it's less than 30 minutes, but.
Well, let's just start with the shortest one because we have people who have to leave in 10 minutes.
Oh, sure.
So have we got something that's shorter, like a 5-minute one? It is important to keep the magnets separated from the filings because unfortunately I see that I did not. And these filings are very difficult to remove from the magnets. Probably not a disaster because there's only a few of them. But
Is there a recommended way to get them back into the shaker?
well, as I say, you have if the magnets are kept on the other side of the paper, then you can simply remove the magnets perpendicular to the paper. And then once the magnets are far away, then you've got, you know, basically the filings are inert, so you can just bend the paper into a funnel and scoop them back in.
Link I put in there is about a 2-minute video, and it just kind of goes through in short and sweet.
Okay, do people see the video now?
Yep, that's the one.
This is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray. And he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam?
Wow.
This appears though it's happening to it. It's moving, it's being repelled, isn't it, by the magnet? We flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles. And he found that these particles were about 2,000 times lighter than a hydrogen atom. Now, at the time, that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound? Because hydrogen's the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron.
Maybe we can see this in another video. But what Thomson was doing was that he was crossing a magnetic field and an electric field. So if you have a known magnetic field and put something through it and it deflects a measured amount, then you know that there is a V cross B force. If you then put an electric field to counteract that, in other words, the magnetic field is pushing it, let's say, down, and you apply an electric field that balances that, you can get a ratio of the electric charge on that particle to its mass. It falls out right out of the bounds between these two forces. So that's what J.J. Thomson did, knowing that the charge was equal to the elementary charge. That's what led to this astonishing result that this was we know today 1,800 times less massive than the hydrogen atom. And this was one of the first steps to the revolution that in physics that occurred at the end of the 19th and the beginning of the 20th century, because people like Maxwell had been striving to explain what the chemists already understood about atoms. And all of a sudden, we had this extreme curveball, that something that was 3 orders of magnitude less massive was not only existed, but they rapidly learned that that was, in most cases, the carrier of electric current. Not all cases. Ions can carry electric current as well. So this, as I explained in the last lecture session, this pretty much put an end to the initial effort to put together the particle nature of atoms with the field nature of electromagnetism. And the relationship of the particles to the fields actually a century later remains, more than a century later, remains an open question. But that experiment with the cathode ray tube is the start of that. So, Brian, do you have another video that actually demonstrates the E-cross, the electric and magnetic field experiment?
So what I'm going to show you today is how they figured out that Dalton's model was not complete. And it began with this thing called a Crookes tube. Anyone seen a Crookes tube before? This is a Crookes tube. What it is it's a tube of glass that's mostly evacuated, meaning most of the air is taken out of it. It's got an electrode on this side and an electrode on that side. Look on the inside of it, there's a white screen, and the white screen is there for reasons I'll show you in a moment. This is a Tesla coil. Tesla coils generate lots of voltage. Right now there's a magnet inside of here that's spinning, and it's got some wires around that magnet. It's generating a lot of voltage as it spins. It's a strong magnet. In fact, if I hold another magnet up here, I can feel it vibrating from the spinning of the magnet. Kind of like your rumblers on your game controllers. And but this is generating a lot of electricity. You can see that if you hold it up to something metal. People always ask what will happen if you touch it. And the answer is you'll die. Why I am now dead. A little bit uncomfortable. But in any case, here's what happens when you hold it across the Crookes tube. I see that? You can see it over there on that side. Everybody see it? Yeah, pretty cool. I actually can't see it from my side, but I assume you're seeing a straight green line. Mostly. Because I'm looking from behind. That white screen's only on the front. It's set up to be viewed from one side only. All right. Now, this is kind of interesting. Watch this. Anything happen? Yeah. What's happening? It's following the magnet, reacting to the magnet, deflecting the magnet. Okay, so that's kind of interesting. Keep that going. I got a one other thing to compare that to. I have light here, and I'm going to pass this light. It's a laser light, green laser light up. There we go. See it? You see that that laser light? Is there? What will happen to it when I get it close to the magnet? What's the way? So. Has no effect on the magnet. The magnet has no effect on it. So why does some light get deflected by a magnet and some other light doesn't? Why is that? What's the primary difference? Why? The answer is, does anybody know what is different about that light from this light? Why are they different? What's one have that the other doesn't? Yes. The specific word we're looking for here. Oh, batteries are electricity, but you kind of got the right word there. Charge is the key. It turns out that this light isn't charged at all, it's just light. This is obviously charged because that's what magnets do, is they deflect charges. They'll either make things go towards them or away from them, depending on plus or minus or the north or south pole of the magnet. And so what we have discovered here is that there's something going through here that is charged. Something's jumping out of this metal electrode into this metal electrode that is charged. And since these metal electrodes are made of atoms, then atoms must have something charged in them. And J.J. Thomson is a scientist on our paper that we researched. This is what he discovered. He discovered that these things, the atoms had these charges inside them called electrons. Those are actually electrons going across there. And J.J. Thomson discovered them.
He still didn't actually show the cross fields. We may have to do that again next time if we can find it. By the way, Brian, why can't we buy a Crookes tube?
So most of the Crookes tubes that are available are only available from China, because actually here in the United States they have a provisional law that has to do with high voltage. Although it's not really dangerous, it can be used to make other stuff that they have deemed to be terroristic in nature. So all local distributors here in the United States, unless you are a school or an educational entity, cannot procure them very easily. However, in China, they have no such stipulations. You just basically have to get it through customs and then you can get one. If somebody wants to get one, I've found multiples of the Crookes tubes on here for anywhere between like $60 and $80, or they have full sets that have differing Crookes tubes with differing experiments on them. A whole set of those is about $500 to $600.
Okay, well, yes. After the sessions, just send me the links to the $60 ones. We're not going to spend hundreds of dollars on this, but
right.
I'd be willing to lay out 60 and see whether we could duplicate the experiment, because as I say, this is certainly one of the most important single experiments in the 19th century, and really did start the very rapid development of our understanding of what atoms consist of. Because when you, as I say, when you look at it, the date of this experiment was, I believe, 93, and the discovery of the neutron, again, to the nearest year approximately, was, I believe, 32. So you have a period of 4 decades in which you went from zero knowledge of the main constituents of atoms, of which we are all consist of, to understanding the basic, the 3 basic constituents, which are electrons, protons, and neutrons. So this was the first step. So those are the conclusion of the demonstration. So basically, any questions or general discussion? So let me just talk a little bit about where we're going next. I am trying to be chronological, to follow the evolution of physics the way it actually occurred historically. So we're going to go back and look at a second extremely important aspect of physics that was developed in the second half of the 19th century, which is the study of thermodynamics, the study of heat and energy, and specifically the development of Boltzmann's theory, because that is a key part of the puzzle. First of all, it's a key part of what allowed the first step in the transition to a quantum understanding of atomic physics. Was you needed to know statistical mechanics and thermodynamics for Planck to actually get to the hypothesis of the quanta. And second of all, as we'll see, the understanding of thermodynamics and entropy that developed at the end of the 19th century posed part of the paradoxes that only deepened as the revolution that was started in the 1890s with the discovery of the electron, the discovery of radioactivity, and the discovery of X-rays and gamma rays. That paradoxes were not actually begun to resolve until the second half of the 20th century. So I'm not ready to give you the readings, but I will be giving you the readings. And I'm not ready to discuss the date because I am incredibly busy, but it will be sometime, it probably will be sometime before Thanksgiving in the United States. So sometime before the end of November. And we are a little bit smaller than we were during the summer, so I will write letters to people whether they were confused about the date or what. But we will be putting the video up for the people who missed it fairly shortly. Oh, actually, I did have one more item to discuss, which was our progress in the lab. I just wanted to show people the very fresh images that we got that showed this basic process in which the electrons moving through our device create magnetic fields that form filaments. And these filaments we want to form because they're the first step in creating the dense hot plasmas that create fusion. So this is a close-up. So first of all, the camera taking this, called an ICCD camera, takes very short exposures. This is a 20 nanosecond, 20 billionths of a second exposure. In theory, the ICCD can go down to a 1/5 of a nanosecond, although I think our device probably no longer can. It's 15 years old. What we're looking at here is a single centimeter wide view of the pulse as it's moving down the anode. So this is at a tilt. The direction of these black lines is actually vertical. And let's see, can people see my mouse, my cursor?
Yes.
Yep.
Okay. So we're looking between two veins, which are the outer electrode. So this here is one vein, and this is another vein. And between those veins, we're seeing towards the anode. This is the front of the current sheath. And these are filaments which actually were initiated off screen at the cathode, where we have little pointy teeth, which are intended to initiate the cathode, the filaments in an organized fashion. What you're seeing here is that the filaments are in the process of getting somewhat disorganized or disrupted. And you can see this is the leading edge, and the leading edge has gotten is no longer straight, it's kind of irregular. If I go to, this is the last shot we took. If I go to the next to the last shot, now I know this looks pretty similar, but what we're seeing here is that the filaments are less disrupted at the same point. And generally we're getting a smoother front line. Now this may not look like too much, and the filaments are a bit stronger. But this shot 2, created 10 times the fusion yield of shot 3. And what Syed and I know is a big difference is simply that in shot 2, the two gases that we were using to mix together, which was nitrogen and deuterium, were well mixed. And in shot 3, they were not well mixed. And frankly, I was very surprised by this discovery because naively I thought mixing was just not a problem. But when we learned that it was a problem, I did some calculations and I realized that, yeah, it makes a big difference whether you put the small amount of nitrogen in first or the large amount of deuterium. So what I'm illustrating here is that the basic concepts that we've just been learning about from over 100 years ago are the basic concepts that we used together with the discoveries of the late 19th and 20th century to understand plasmas that could be creating the next energy source for the entire world. So these concepts have aged very well. Any questions?
How do you calculate the optimum separation of the filaments initiation?
Yes, well, that's a really good question. It's not obvious from the equations what the optimal number of filaments are. When we started the project back in 2009, we actually had the idea that we should have about 100 filaments. And we actually set up little tungsten pins, they were quite tiny, to create these filaments. And we were pretty shocked to see that, of course, tungsten is the element that has the highest melting point known to science. And after a few shots, these little tungsten needles were simply being worn away. They were getting they were melting and then vaporizing. So we went through a number of iterations until we got to these much more robust teeth. And in the course of this, we have a colleague in the UK, Warwick Dumas, who was doing a fairly simple simulation of the heating of these filaments. And we realized if the filaments were that close, because there was 100 of them around this rather small anode, they would heat up very rapidly and collide with each other. So that wasn't good. So when we switched to the more robust teeth, so these are teeth initially of tungsten, now they're of beryllium, which, are like at a right angle. They're a little more complicated. We made only 32 of them. Now, because of conservation of angular momentum, these filaments occur in pairs. So 32 teeth was going to lead to 64 filaments. Well, when we started running these machines and we saw these pictures, there was a problem, because if you count these filaments, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 9.5, for every vein. So this is a gap between the veins, but of course there's as many gaps as there are veins. You have 8 or 9 filaments. There are 16 veins, 32 teeth. For every vein, we expected 4 filaments. And I sort of embarrassed to admit this, but for a long time, I could not figure out why we were getting twice as many filaments, basically the same number of filaments we started with. But as I'll explain in a future report, I realized that the shape of the tooth did not take into account the actual field direction at the start of the pulse, and that the pulses were starting on the ridges that led to the tooth, and the ridges were also sharp. So actually we were getting 2 sources of filaments for every tooth, which adds up to 4 filaments per tooth, or back to 128. So we still, in a future iteration, will probably need to get down to 64. We also have done calculations subsequent to all this that indicates if you get too few filaments, when we get up to our full power, which is 2.4 megaamps, we could have too much current concentrated on the anode. And if too much current is concentrated in too small a place by these filaments, we couldn't melt the beryllium anode. So there has to be a compromise. 32 was probably too few. 128 is definitely too many. So we have to get back to what was our original aim, which was 64. So the basic answer is we've sort of arrived at the optimal calculation, but it took us quite a while to get there. So we are running out of time. Oh, Brian, you did have a question. You can have the last word.
Oh, I was just going to say, so basically your chamber is basically a very expanded upon version of a Crookes tube then.
Well, without the fluorescence screen, right. In a Crookes tube, you have a closer to a real vacuum. We actually have a filling gas that has a significant pressure. So we pump down to a high vacuum of a few microtorr. So the atmosphere we're breathing right now is 750 torr. So we're pumping down to a billionth of an atmosphere, which is a vacuum. But then we fill it with the gas that we need to create the fusion. And we fill it considerably. These experiments, we have 40 torr. So that's about a 20th of atmospheric pressure. So that's much greater pressure than in a Crookes tube. But it is a form of, it's obviously a form of electric discharge, but not a true vacuum. So let's call it a day, and I'll get back to you by email about the next readings, which will be on the 19th century development of thermodynamics.